lot of gas samples are mixtures of different gases rather than just a single gas. Air is an example, and here we're talking about dry air. What makes something wet? Water, right? The air that we're breathing right now has some water in it. We call it humidity, right? So right now, the humidity in here is 56%. And someone yesterday said, well, why is that so much higher than it is outside? Because of all of our bodies. We're exhaling, and when we exhale, it's not only carbon dioxide, there's also water vapor. And then if you're like sweating and your sweat's evaporating, anywhere there's a bunch of people, you're going to have higher humidity right there. So this is dry air without the water. So dry air is mostly nitrogen. 78% of the volume of air is nitrogen. 21% is oxygen. So air is mostly just nitrogen and oxygen. And then there's a little bit of argon, which is kind of exotic, and a little bit of carbon dioxide. It's 0.04%, but turns out, it's important, right? We don't want it getting too high.
Is it possible then, if you have enough people in a room, to drown? Because they release enough?
Is it possible to drown if you had enough people in the room? No. You could get to 100% humidity, though. And that would be kind of like a sauna, right? A steam bath. Yeah, not very pleasant. I grew up in the Midwest where, the day we got married, it was 95 degrees and 95% humidity. And people coming to the wedding from like Phoenix, they get off the airplane into the airport and they're like, oh, I can't breathe. It's like walking into a wet blanket. Like you're walking through a wet blanket. I think Fresno's kind of a nice compromise in humidity. It's not so dry that you might die going for a walk if you didn't bring your water bottle. But you're not going to suffocate either. So you might feel like you're suffocating in 100% humidity, but you're not. So I've mentioned this before. Gases are different than solids and liquids because we can think of a mixture of gases as just being a single gas because the individual particles, the individual gases act independently of each other, like the other gas isn't even there. So air is a mixture, but we can measure the pressure, volume, and temperature of air as if it was a pure substance. If we use pressure, volume, and temperature to calculate the moles of air, what we're getting is the moles of nitrogen and oxygen and the argon and the other things. Okay? Because gases behave independently. So each gas in a mixture is going to have its own pressure. It will exert a pressure on its container. And the total pressure is the sum of the pressures from all of the individual parts. Like let's say we had a box and we put some oranges and some bananas. If you knew the mass of the oranges and the mass of the bananas, you could find the mass of all of the fruit, right? You would just add them together. It works the same way with pressure for gases. We've got the pressure from the nitrogen and the pressure from the oxygen, and so the total pressure is the sum of those. So the individual pressure of one gas in a mixture is called its partial pressure because it's part of the total pressure. And we can calculate that partial pressure from the ideal gas law. So, PV equals nRT. If we want P by itself, we're going to divide by V. So the pressure of gas N is equal to the number of moles times R times the temperature divided by the volume. Even though that one gas is just part of what's in there, it still occupies the full volume. So all the gases in there have the same volume because they can go through each other, right? Because they're mostly empty space. It's not like, bananas and oranges where they can't be in the same space. Gases can do that. So Dalton's law of partial pressures says the sum of the partial pressures of all the gases in the mixture equals the total pressure. So the total pressure of a gas is equal to the pressure from gas A plus the pressure from gas B plus the pressure from gas C. Keep going as many gases as you have. So the total pressure is the sum of the partial pressures. Each of these partial pressures is the moles of that gas times RT over V. And so the pressure from B is moles of B times RT over V, etc. The R, the T, and the V are the same for all the gases. And so here they've just factored that out. So we've got moles of one gas plus moles of another gas plus moles of the other gas, etc. And that gives us the total number of moles of gas times RT over V. I'm not going to make you do this derivation on an exam or anything. So if we look at the ratio of the pressure from one gas to the total pressure, the pressure from one gas is the moles of that gas times RT over V. The total pressure is the total number of moles times RT over V. And the RT, V cancel out, leaving us with moles of A over the total number of moles. The part over the whole. And that's called the mole fraction. The mole percentage would be moles of A over total moles times 100. That would be the mole percentage. That's not what we're using here. This is the mole fraction. It's this part before you multiply by 100. And its symbol is chi, as a funny X. It's a Greek letter chi. Chi sub A. This is the mole fraction. So it's the fraction of the gas that is that one individual gas. So down here what they're doing is they're rearranging this, the partial pressure, so they multiplied both sides by P total, and then this is the mole fraction, so they're calling it chi, and we end up with this. The partial pressure of a gas is equal to its mole fraction times the total pressure. So if you think of a gas maybe that only has two gases in equal amounts, each gas is 50% of the total. And the total pressure is 1 atmosphere. Well, each gas is going to be 50% of the total, or 0.5 times the total. So each gas will be 0.5 atmospheres, and they add up to be 1. So the partial pressure of a component in a mixture is its mole fraction times the total percentage. When we were talking about the air, we were looking at percentages. Nitrogen has a 78% composition in air, or air is 78% nitrogen. Somehow those words suddenly just don't make any sense to me. The percent by volume would be the same as the mole percent. So to get the mole fraction of this, we divide by 100. So the mole fraction of nitrogen is 0.78 in dry air. If the total pressure is 1 atmosphere, that means the pressure exerted by nitrogen is 0.78 atmospheres. I don't like this example, but we're going to do it. To prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. So you've got something that's so reactive that, you can't have it, just under water or under oil. It's going to react with pretty much anything. It'll react with the air. So how do you keep this stuff from reacting? Well, you have to surround it with something that is not going to react with anything, like a noble gas. So you've got this reactive thing, and then you flush noble gases. Here's a mixture of helium, neon, and krypton through the container until you get all the air out, and then you seal it up. And now the reactive chemical can't do anything because the noble gases won't react. So a chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15 grams of neon, 35 grams of krypton in a piston cylinder assembly at STP. And we're supposed to calculate the partial pressure of each gas. Well, let's highlight what we know. 5.5 grams of helium, 15 grams of neon, 35 grams of krypton. STP. It's really easy to overlook that. That tells us the pressure and the temperature, which is, we need those things when we're dealing with gases, right? And then they're saying calculate the partial. Okay, the same thing happened yesterday. Somehow it got paused. I don't know where it left off. Oh dear. Anyway, the partial pressure of helium would be the mole fraction of helium times the total pressure. Do we know what the total pressure is? It's one atmosphere, STP, 1 atmosphere. So we need to find the mole fraction of each of these gases. So the mole fraction of helium is going to equal the moles of helium over the total number of moles, which is helium plus neon plus krypton. They gave us masses. Of course they did. So we need to convert and calculate the moles of each gas. So 5.50 grams of helium. We want moles. We're going to divide by grams. And this isn't hard, it's just tedious. So helium, 4.003. 5.5 divided by 4.003, 1.37. So I told you not to round things on intermediate calculations. We're going to do it anyway on this one because it's just so many numbers. So that's the neon, the helium. Helium, it's helium. Neon, 15 grams of neon. Converting to moles, dividing by grams, neon 20.18. So 15 divided by 20.18. 0.743. And then krypton, 35 grams. multiplying by moles, dividing by grams, grams cancel out. Krypton is 83.80. 35 divided by 83.80. 0.408 moles. So that's the moles of each individual gas. What's the total number of moles? Well, we're going to add these up, right? To get the total moles. 1.37 plus 0.743 plus 0.408 equals 2.521 moles. So that's the total number of moles. So now we can calculate the mole fraction for each of these guys. So mole fraction for helium equals the moles of helium divided by the total moles. The moles cancel out. 1.37 divided by 2.521. 0.543. No units, because they went away. And then for neon, mole fraction for neon is the number of moles of neon divided by the total. .295. And then the mole fraction of krypton is the number of moles of krypton divided by the total number of moles. .162. So we found the mole fractions, but we want the total pressure. The total pressure is the mole fraction. So we want the partial pressure for each gas. We want the pressure for each gas. It's the mole fraction times the total pressure. Well, the total pressure is 1 atmosphere. So the partial pressure of helium equals 0.543 times 1 atmosphere. So here the mole fraction is equal to the partial pressure because the total pressure is 1. So here 0.295 times 1 atmosphere is going to be 0.295 atmospheres. And 0.162 times 1 atmosphere is 0.162. If we add these up, they should equal the total pressure. If we add the mole fractions up, they should equal 1. Ends up being the same thing. You add them up, you get 1. Any questions? Like I said, I don't really like that example. A gas mixture contains an equal number of moles of helium and neon. The total pressure of the mixture is 3 atmospheres. What are the partial pressures of helium and neon. The partial pressures are related to the number of moles, right? So here it says they're equal numbers of moles. So then what would be the percentage split between helium and neon? Be 50-50, right? You've got this total thing, and it's an equal number of both things. There's two things, so it's 50% one, 50% the other. So then the mole fraction is 0.5. They're going to exert equal pressures. So what are the pressures going to be? They're both going to be 1.5. All of these choices, the pressures add up to 3. But here, the pressures are equal because they have equal numbers of moles. Any questions? Here we have a sample of hydrogen gas mixed with water vapor. The mixture has a total pressure of 755 torr, and the water vapor has a partial pressure of 24 torr. What amount in moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 K? So I'm going to highlight the numbers. No, that's not the highlighter. This one and this one and this one and this one. And then the question is, amount in moles of hydrogen. So if we think about this, we have a total pressure of the gas, which says is 755 torr, and the total pressure is equal to the pressure from hydrogen plus the pressure from the water vapor. They both contribute. They tell us what this pressure is. The pressure of the water is 24 torr. So 755 torr is equal to the pressure of hydrogen plus 24 torr. So the pressure of hydrogen is 755 minus 24, which is 731 torr. Does that make sense? There's several questions in the worksheet that talk about some gas and water vapor. And they give you the total pressure, and they'll give you the partial pressure of the gas, of the water vapor, or make you go look it up, and then you have to subtract. So this is the pressure of the hydrogen gas. We're trying to find the moles of hydrogen, not the total moles of gas. So we have to use the pressure of the hydrogen. And the volume is 1.55 liters. The temperature is 298 K. Well, that's nice. At least those were in the correct units. But again, we have to convert torr to atmospheres. Remember, torr and millimeters of mercury are just different names for the same thing. So this is 0.961 atmospheres. The volume is the volume of the whole thing. Both of the gases have the same volume, which is really kind of trippy when you think about it. The temperature is the same, but the pressures are different. So we found the pressure of the hydrogen gas, and now we can calculate the moles using the ideal gas law. PV over RT. So pressure 0.96184 atmospheres. And the volume 1.55 liters divided by 0.08206 liter atmospheres per mole Kelvin times 298 Kelvin. And again, that's going to have 3 sig figs. 0.0610 moles. I'm keeping this 9, and the 6 tells me I have to round the 9 up to a 10. So this becomes a 1, and that becomes a 0, and that's our answer. Any questions? We talked a little bit about going underwater at the beginning of the chapter in relation to pressure. So when someone does deep sea diving, because the pressure of the water gets really great as you go down deep, you need pressurized air in order for you to be able to breathe. So if you breathe compressed air, then you're going to have a high partial pressure of oxygen, and you're going to get an increased amount of oxygen in your blood. You might say, well, it's a good thing, right? Oxygen's good for you, but too much oxygen is bad for you. Oxygen toxicity occurs at oxygen partial pressures above 1.4 atmospheres. So above 1.4 atmospheres up here, you're getting into a dangerous place with too much oxygen. And then you can also have hypoxia, which is hypooxygen, right? Below low oxygen, or oxygen starvation. And that's going to be below, down in low concentrations, low partial pressures. If you're breathing compressed air, you get more oxygen, you also get more nitrogen. And if we have high nitrogen pressures, above 4 atmosphere, you can get something called nitrogen narcosis. It's also called rapture of the deep. That sounds romantic, right? Ooh, rapture of the deep. It's like getting drunk. So it's like you're drunk on nitrogen, right? You have impaired judgment. Your motor skills are not good. This is not a safe thing when you're far down under the water. So to avoid that, because what will happen here, up at the surface, air has a total pressure of 1 atmosphere, 0.78 atmospheres nitrogen, 0.21 atmospheres oxygen. 30 meters, the compressed air has to be 4 atmospheres, and so now you've got 3.12 atmospheres of nitrogen and 0.84 atmospheres of oxygen. So they're both going up. So how do you avoid getting too much nitrogen? Well, you breathe something besides air. You mix oxygen with something else that isn't going to give you rapture of the deep. So heliox is one of those mixtures. It's helium and oxygen. And so you can get the oxygen without the nitrogen. The helium doesn't really have any effect on you, except it makes your voice really high. But you can't have any fun with that underwater, so it's kind of cool. So a diver breathes a heliox mixture with an oxygen mole fraction of 0.05. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? So what do we have here? We have oxygen mole fraction, and we have partial pressure of oxygen, and they're asking us for the total pressure. So mole fraction of oxygen is 0.050. The partial pressure of oxygen is 0.21 atmospheres. So an equation we learned about today is that the partial pressure of one of the components is equal to its mole fraction times the total pressure. So we know this one, and we're looking for this pressure. So we'll divide both sides by the mole fraction. And our total pressure will equal the partial pressure of oxygen divided by the mole fraction of oxygen. So 0.21 atmospheres divided by 0.050. 4.2. Questions? So if you have a chemical reaction that's generating a gas and you want to measure the gas, how do you catch it? Because, like when we did dissolve the copper wire in nitric acid, NO2 was given off. We saw the brown smoke and it just kind of floated up into the hood and went away, right? How do you catch it? Well, a common technique is called collecting over water. So you would do your reaction in a closed container, and there would be an opening to a tube where the gas could travel down through some water and up into an inverted container containing water. So this looks a lot like that mercury barometer, right? Except this is water instead of mercury. So you would start this out by filling this container, it kind of looks like a beaker, I think. Fill this beaker with water and invert it into this dish of water, and initially there's no gas present. As the reaction generates gas, the gas comes through here and it floats up into this container and starts to displace the water. And it's not going to go down because it's less dense than water, and it can't get out, right? So we've got it trapped. Then we can measure the volume of the gas that we've trapped. We can measure its temperature. We can measure its pressure. The one tricky thing about this is you don't just have the gas that you're interested in. Here it's hydrogen gas, but there's water with space above it, and so the water will start to evaporate. And so you will also have water vapor present there. So anytime you collect a gas over water, you have a mixture of that gas and water. So then to find the pressure of the gas you're interested in, you have to subtract the partial pressure of water. Partial pressure of water vapor is also called the vapor pressure. And it turns out it only depends on the temperature of the water. And so you can go to a table like this and say you've got, your water's at 30 degrees Celsius, then the vapor pressure of water is 31.86 millimeters of mercury. So I could subtract that from my total pressure to get the pressure of the gas I'm interested in. A sample of acetylene is collected over water. The total gas pressure is 738 torr, and the volume is 523 milliliters. At the temperature of the gas, 23 degrees Celsius, the vapor pressure of water is 21 torr. How many grams of acetylene are calculated? So we've got a volume, we've got a temperature, there's a pressure over here, there's another pressure. And we want grams of acetylene. So I'm trying to find grams of C2H2. This is one of those problems where we use an equation and unit analysis, dimensional analysis. What have we been calculating from ideal gas law? Moles of the gas, right? So from the pressure, the volume, and the temperature, we can get the moles of the gas. How can we get from moles of gas to grams of gas? Molar mass. So the moles is PV over RT. But this is a total pressure. If we use that, we'll get the moles of acetylene and the moles of water, and that's not what we want. So the pressure of the acetylene, C2H2, is going to be the total pressure minus the pressure of the water. So that's 738 torr minus 21 torr. And again, that's not in atmospheres. So if you're tired of writing stuff out, let me show you this. So 717 torr times 1 atmosphere over 760 torr. That's what we've been doing, right? And the torrs are going to cancel out. So a shortcut that a lot of people like to do is for the pressure, they'll just write 717 divided by 760 atmospheres. And if that, just doesn't work for you, go ahead and calculate it in atmospheres and write it down. Here's our volume, 523 milliliters. Needs to be in liters. 523 times 10 to the minus 3 liters. .08206 liter atmospheres per mole Kelvin. And our temperature is 23. Well, 23 plus 273 is 296, right? $717 divided by 760 times 523 EE minus 3 divided by, open the parentheses, 0.08206 times 296, close the parentheses, equals. Zero two zero 313 moles. So the moles, that's this part. Now we need to convert to grams. So 0.0201313 moles times multiplied by grams, divided by moles. And the molar mass we get from the chemical equation, 2 times the mass of carbon plus 2 times the mass of hydrogen. .036. So 0.021313 times 26.036. 0.52887, 0.529 grams. Did I do it right? 'Cause I think this is another one I screwed up on last night. Just seeing if they were awake. This example is extremely similar to the previous one. Do you want to see it or not? I'm seeing mostly no. We got this.